In 1970, the Soviet Union started drilling a hole above the Arctic Circle, nearly 8 miles straight down into the Earth's crust. And what they found down there was so fundamentally wrong compared to everything scientists believed about our planet. Because right now, the ice above that hole is melting. The permafrost is cracking open, and the things that were buried down there, the heat, the ancient biology frozen in time, are starting to come back up. So, let's go down. The Soviets chose a spot on the Kola Peninsula in northwestern Russia. It's a bleak, icy slab of land jutting into the Arctic, part of something called the Fennoscandian Shield, one of the oldest exposed sections of continental crust on Earth. Archean and Proterozoic rocks, the kind that were formed when the planet was young before almost everything. They designated the borehole SG3 and began drilling in 1970. The original target was 15 kilometers. They never made it. For the first several thousand meters, things went more or less as expected. The drill passed through Proterozoic rocks, sandstones, tuphites, phyllites, and schists. These are the sedimentary and volcanic layers that were deposited on top of the ancient shield over hundreds of millions of years. The geological record was rich and largely consistent with existing models. But then, as the borehole dropped past 6,000 meters, the problems started. The first major surprise was the absence of the basalt layer. According to seismic data, the drill should have crossed the Conrad discontinuity somewhere around 7 kilometers. That boundary was supposed to mark the transition from granite to basalt. Instead, they found no such thing. There was no basalt layer. The seismic reflections that scientists had been interpreting as a compositional boundary, granite on top, basalt below, turned out to be caused by something else entirely. The reflections were coming from metamorphic contrasts and structural features within the same type of rock. Shear zones, fracture networks, changes in how the rock had been deformed over billions of years. The granite-basalt model of the continental crust, one of the foundational concepts in geology, was wrong, at least here. And if it was wrong here, on some of the most ancient and well-studied crust on the planet, it was probably wrong in a lot of other places too. But that wasn't even the most startling discovery. As the drill continued deeper, temperatures rose far beyond what anyone had predicted. The standard assumption was a geothermal gradient of about 25 to 30 degrees Celsius per kilometer, which would put the temperature at 12 kilometers somewhere around 200 degrees. But the actual readings were significantly higher. At 10 kilometers, the temperature hit 180 degrees Celsius. By the time they reached the final depth of 12,262 meters, the bottom of the hole was 212 degrees Celsius. The Earth was hotter down there than the models said it should be. And that extra heat wasn't just an academic curiosity, it changed everything about how the rock behaved. At those temperatures, the rock began to act less like a solid and more like a thick paste. It flowed. It deformed plastically. Every time the drill bit cut into the formation, the hole would slowly squeeze shut behind it, collapsing under its own pressure and heat. The drill team had to constantly fight the well to keep it open. Eventually, the rock won. In 1992, drilling was officially abandoned. Not because they ran out of funding, although that played a role, but because the physics at the bottom of the hole simply wouldn't allow them to go any further. The rock was alive in a way no one had expected. And then, there was the water. This might be the single most important thing the Kola borehole discovered. Deep crystalline rock, the kind of ancient basement rock that makes up the continental crust at those depths, was supposed to be dry, sealed, impermeable. The prevailing model said that at depths beyond a few kilometers, the immense pressure would crush any pore space, close any cracks, and squeeze out any fluids. The deep crust was thought to be a dead zone, solid, static, and bone dry. It was none of those things. The drill encountered highly mineralized fluids, hot brines circulating through fractured rock at depths of 6, 8, 10 kilometers and beyond. These weren't tiny traces of moisture. These were active hydrothermal systems, fluids moving through fault zones and fracture networks, carrying dissolved minerals, salts, gases. The Poritash fault zone, intersected at around 6 to 8 kilometers depth, turned out to be a major conduit, a superhighway for deep crustal fluids that had been flowing for geological timescales. The crust wasn't sealed at all. It was permeable, it was wet, and it was chemically active. They also found something biologically impossible, or at least, it should have been impossible. At around 6 kilometers depth, the drill pulled up mud containing what appeared to be microscopic fossils, reworked fossil plankton. At first, scientists assumed contamination, but the evidence pointed to something else. The fossils had been transported down into the deep crust by those same circulating fluids carried along fault systems over millions of years. The deep earth wasn't just wet. It was connected to the surface in ways nobody had imagined. Material from the ocean and the biosphere was being pulled into the crust, processed, and redistributed by the same hydrothermal systems that were supposed not to exist. Now, here's where it gets really interesting. Among the fluids recovered from the deepest sections of the borehole were gases, hydrogen, methane, light hydrocarbons. Not the kind you'd expect from a biological source, not the kind that come from ancient dead organisms buried and cooked over millions of years. These were non-biogenic hydrocarbons generated by chemical reactions between water and rock under extreme pressure and temperature. The deep earth was manufacturing its own fuel, but the Kola borehole wasn't alone. Around the same time that the Soviets were pushing the limits on the Kola Peninsula, Germany launched its own ambitious deep drilling project. The Continental Deep Drilling Program, or KTB, was carried out between 1987 and 1995 near Windischeschenbach in Bavaria. The program consisted of a 4-kilometer pilot hole followed by a 9,101-meter main borehole. The temperatures at the bottom reached 265 to 270 degrees Celsius, even hotter than Kola. And the findings were remarkably consistent. The KTB borehole confirmed that the geothermal gradient was steeper than models predicted, about 28 degrees Celsius per kilometer, requiring scientists to rethink their models of how heat moves through the continental crust. They realized that the temperature patterns they were seeing couldn't be explained by simple conduction alone. The heat flow was being influenced by something more complex, by the history of glaciation and deglaciation cycles, by advective fluids moving heat upward through fracture networks, by the same kinds of hydrothermal circulation that Kola had revealed. The crust was not passively radiating heat, it was actively transporting it. KTB also demonstrated hydraulic connectivity at extraordinary depths. Pumping tests between the pilot and main holes showed that fractures were interconnected across kilometers. Fluids could move from one borehole to the other through the rock. The deep crust was, in essence, plumbed. It had a circulatory system. Seismic reflectors that had been interpreted as boundaries between different rock types turned out to be graphite-rich and sulfide-rich shear zones, mineral concentrations that explained both the seismic anomalies and the unexpectedly high electrical conductivity of the deep crust. The signals that geophysicists had been reading from the surface and interpreting as layers of different rock were actually something completely different. They were fluid-filled fractures, mineral concentrations, and deformation fabrics. But perhaps the most dramatic experiment at KTB involved injecting fluid into the borehole at around 9 kilometers depth and 260 degrees Celsius. The scientists pumped water into the crust and listened. What they heard was hundreds of micro-earthquakes, over 400 of them, triggered by pore pressure changes of less than 1 megapascal. The crust, at those depths, was critically stressed. It was balanced right at the edge of failure, like a shelf loaded with books where one more paperback causes the whole thing to collapse. The deep earth wasn't stable. It was tense, pressurized, barely holding together, and something as small as a slight change in fluid pressure could trigger fracturing. That discovery had enormous implications. It meant that the deep crust responds to fluid changes almost instantly. It meant that natural processes like hydrothermal circulation, chemical reactions between water and rock, even slow tectonic movements could trigger earthquakes at depth. And it meant that human activities, things like injecting fluids for geothermal energy or carbon dioxide storage, could do the same. The KTB project also established something that has shaped every ultra-depth operation since. The crust, at depths approaching 10 kilometers, is what geologists call critically stressed. It maintains a state of Coulomb failure equilibrium, which is a technical way of saying that the forces trying to break the rock apart and the forces holding it together are almost perfectly balanced. The friction that keeps faults locked, described by something called Bailey's law, operates at a coefficient of about 0.6 to 1. And pore pressures at those depths remain closer to hydrostatic than to lithostatic, meaning the fluids are under the pressure of the water column above them, not the full weight of all the rock. This was a critical insight because earlier models had assumed near lithostatic overpressures deep in the crust, which would have implied a fundamentally different mechanical state. The reality was more delicate and more dangerous. What happens when you combine critically stressed rock with chemically reactive fluids? You get something called chemomechanical feedback. At temperatures above about 200 degrees Celsius, which you hit well before 10 kilometers in many continental settings, reactions like serpentinization and carbonation begin to occur in mafic and ultramafic rocks. These reactions involve water reacting with iron-bearing minerals, and they produce new mineral phases that take up more volume than the originals. The expansion can be enormous, increasing solid volume by 40 to 50% and generating crystallization pressures that exceed 300 megapascals. That's far greater than the typical differential stresses in the mid-crust. These pressures can fracture intact rocks, reopen sealed microcracks, and sustain fluid pathways over geological timescales. Cores recovered from both Kola and modern Chinese wells contain dense networks of serpentine veins, carbonate veins, and sulfide minerals, along with shattered feldspar and partially altered olivine, all directly confirming that chemical reactions are driving mechanical failure deep in the Earth's crust. And these reactions are temperature-dependent. Serpentinization-related failure peaks near 260 degrees Celsius. Carbonation peaks near 185 degrees Celsius. Both occur within the temperature ranges recorded in boreholes deeper than 9 to 10 kilometers. The rock cannot creep fast enough to relax the stress, so brittle failure dominates. The deep earth cracks itself open from the inside out, driven by its own chemistry. The practical lesson from both KTB and Kola is sobering. Future drilling operations at these depths must incorporate continuous downhole stress imaging, real-time pore pressure tracking, and sophisticated thermal hydraulic modeling to anticipate what the rock is going to do next. Small pressure oscillations during routine operations, even just circulating drilling fluid, can trigger fault slip on optimally oriented fractures. And chemically reactive zones, especially where hydration or carbonation is actively occurring, can rapidly destabilize wellbores unless casing programs and drilling fluid formulations are adapted to the evolving conditions. The deep earth is not a passive medium you drill through. It is an active system that pushes back. Now, decades later, the world is drilling deeper than ever, and what they're finding is rewriting the rules again. In China's Tarim Basin, in the northwest of the country, a well-designated SDTK-1 reached 10,910 meters in depth. Bottom hole conditions were roughly 220 degrees Celsius and pressures exceeding 145 megapascals. It was completed using the world's first 12-kilometer rated automated land rig. The well crossed 12 stratigraphic units, from Cenozoic sediments at the surface all the way down through Mesozoic and Paleozoic layers into Cambrian rocks that are over 500 million years old. And the reason this matters is what they found at the bottom. Classical petroleum system models have long assumed that oil can only exist within a specific temperature window, roughly 60 to 160 degrees Celsius. Gas can survive a little deeper, up to maybe 200 degrees Celsius. Beyond that, the thermal energy is so intense that hydrocarbon molecules break apart. Oil cracks into gas. Gas cracks into carbon and hydrogen. Everything eventually becomes graphite. That was the conventional wisdom. Oil and gas have a depth limit, and beyond it, there's nothing useful left. SDTK-1 proved that wrong. In August 2025, the well achieved the first confirmed commercial-scale hydrocarbon flow from depths exceeding 10 kilometers. Tens of thousands of cubic meters of natural gas per day, flowing from Cambrian strata that are older than most complex life on Earth. But before we get into the details of what China found, it's worth noting that hints of this discovery had been appearing for decades. Back in the 1970s, in the Anadarko Basin of Oklahoma, 2 American wells set world depth records before being surpassed by Kola. The Lone Star Baden well reached 9.16 kilometers in 1970, and the Bertha Rogers well reached 9.58 kilometers in 1974. Both encountered temperatures exceeding 200 degrees Celsius and pressures approaching 250 megapascals, conditions that were thought to be well within the territory of low-grade metamorphism. Yet the rocks did not behave as expected. Sandstones showed burial-related textures, but no metamorphic mineral assemblages. Carbonates deformed plastically, but didn't recrystallize into new metamorphic phases. And dollarstones preserved up to 20% porosity at 7.9 kilometers, demonstrating a resistance to compaction that challenged everything geologists thought about deep burial. The most striking find from the Bertha Rogers well was the presence of liquid hydrocarbons at depths and temperatures where only methane or graphite should have existed. Geochemical analyses identified significant concentrations of heavy paraffins, condensates, and anomalous bitumen. The conclusion was unavoidable. Hydrocarbons can survive and even be generated at far greater depths and temperatures than the textbooks allowed. The type of organic matter, the mineral environment, and the pressure regime exert stronger control on what survives than temperature alone. These findings sat in the scientific literature for decades, largely overshadowed by more conventional exploration. But they were signals, early warnings, of what China would later confirm at scale. The gas composition data from SDTK-1 tells a remarkable story. In the upper sections, around 8,500 meters, the gas was wet and mixed, containing methane alongside heavier components like ethane, propane, and butane, a liquid-rich condensate system. But as the well went deeper, past 10 kilometers, the gas became progressively drier. Methane climbed to over 92%. Heavier hydrocarbons disappeared almost entirely. And in the deepest zones, below 10,700 meters, the gas was nearly pure methane, over 99%, defining a dry gas end member at depths that were supposed to be well beyond the point where petroleum systems could survive. The carbon isotope data confirmed what was happening. The methane was getting isotopically heavier with depth, a signature of advanced thermal cracking. The original oil had been cooked so intensely that it broke down into methane and left behind a solid residue called pyrobitumen, a kind of fossil tar. But the methane itself was stable. It persisted. It accumulated. It formed a commercial gas reservoir at depths where textbooks said nothing should exist. And that's not all. The source rocks in the Thawing Basin, the organic-rich formations that originally generated the hydrocarbons, were still detectable at over 10 kilometers. The Lower Cambrian Uatusi Formation, logged in the SDTK-1 well, contained 52 meters of effective source rock with organic carbon content up to 6%. Despite being buried deeper than nearly any other source rock on record, despite being over-mature by every conventional measure, it still retained geochemical signatures of hydrocarbon generation. The kerogen, the ancient organic matter from which oil is born, was not destroyed. It was transformed, yes. Cooked to the point of exhaustion, yes. But it left a chemical fingerprint that scientists could still read 500 million years later from 10 kilometers below the desert. The reservoir rocks were equally surprising. Dolomite formations in the Cambrian shale-like formation preserved porosity at over 10 kilometers depth, intercrystalline pores, dissolution vugs, fractures, 96 meters of effective reservoir holding gas in rock that should have been completely compacted and sealed. The early diagenetic processes that formed these rocks, the way they were shaped by ancient seas and microbial mats hundreds of millions of years ago, had given them a structural resilience that outlasted everything the planet could throw at them. Pressure solution and clay-rich laminae locally reduced porosity, but the overall carbonate system held. The rock remembered its origins. China's second ultra-depth well, X1, drilled in the Jungar Basin, reached even deeper, 11,156 meters. Together, these two wells confirmed something that changes the global energy map. Petroleum systems can persist well below 10 kilometers. They are not bounded by the temperature limits in textbooks. Pressure, mineral surfaces, water-rock reactions, and confining stress all modify the kinetics of hydrocarbon breakdown. The deep earth is not a crematorium for oil and gas. Under the right conditions, it is a preservation vault. And the implications extend beyond fossil fuels. The same deep drilling technology that found gas at 10 kilometers is now being repurposed for something else entirely: geothermal energy. The boreholes at Kola and KTB showed that the deep continental crust stores and transmits both heat and fluids. Modern enhanced geothermal systems aim to exploit this by drilling into hot, dry, crystalline rock at depths greater than 5 kilometers, creating artificial fracture networks and circulating water through them to extract heat. In principle, this energy source is limitless, zero carbon, and available everywhere on the planet. The heat is always there. You just need to drill deep enough to reach it. China's Songliao Basin drilling program offers a preview. The SK2 borehole recorded downhole temperatures exceeding 150 degrees Celsius at about 4.4 kilometers, corresponding to a heat flow of roughly 84 milliwatts per square meter, a clear indicator of hot dry rock geothermal potential. At about 7 kilometers, the drill intersected a pre-Mesozoic metamorphic complex of mylonites, cataclasites, and fractured rock, documenting both regional and dynamic metamorphism, and confirming that the crustal conditions necessary for geothermal exploitation exist at accessible depths. For countries with existing oil and gas expertise, this represents a strategic pivot. The same directional drilling skills, the same high-pressure well control systems, the same geotechnical engineering knowledge that built the modern petroleum industry can be redirected toward geothermal energy. Canada, with its deep petroleum drilling heritage, is particularly well positioned. But the challenges remain formidable. Extreme downhole temperatures degrade electronics, logging tools, and rotary steerable systems. Corrosive brines and acidic fluids attack steel. Low permeability in deep rock requires reliable stimulation techniques, and drilling costs escalate steeply beyond 7 to 10 kilometers. Future advances in laser or plasma drilling, high-temperature electronics, corrosion-resistant materials, and AI-driven monitoring may eventually make routine access to depths of 10 kilometers or more economically viable. If they do, geothermal energy could transform from a niche resource into a cornerstone of global decarbonization. But hydrocarbons and geothermal heat are not the only things hiding down there. Among the most remarkable findings from both the Kola borehole and the modern Chinese wells is the presence of hydrogen, natural hydrogen, not manufactured, not pumped in, generated by the Earth itself. In the Kola Superdeep Borehole, fluids recovered from depths greater than 11 kilometers contained up to 20.8% hydrogen. At KTB, concentrations reached 8.6% at about 9 kilometers. In China's Songke, two scientific borehole in the Songliao Basin, hydrogen anomalies of up to 2.39% were detected at depths between 2.8 and 6.8 kilometers. And in legacy mining wells in France, scientists found 26 hydrogen-bearing intervals, with concentrations reaching 52% in the Dogger aquifer of the Paris Basin. This hydrogen comes from multiple sources. In ultramafic rocks, a chemical reaction called serpentinization produces hydrogen when iron-bearing minerals like olivine react with water. It's a slow, continuous process that can sustain hydrogen generation over thousands to millions of years. In granitic rocks rich in uranium, thorium, and potassium, radioactive decay splits water molecules apart through a process called radiolysis, producing hydrogen continuously over hundreds of millions of years. And in overmature organic-rich sediments, the extreme breakdown of kerogen at very high maturity levels releases hydrogen as a byproduct of aromatization and methane cracking. These processes mean that the deep Earth is manufacturing hydrogen right now, beneath our feet, all the time. And while global estimates of in-place hydrogen resources may reach staggering quantities, possibly on the order of 5.5 million megatons, the practical questions of whether it can be extracted, stored, and used remain open. The significance of natural hydrogen extends beyond its potential as an energy resource. Hydrogen is also emerging as a powerful tracer of deep Earth processes. Helium, which often co-occurs with hydrogen in deep fluids, carries isotopic signatures that fingerprint its origin. The ratio of helium, 3 to helium, 4, reveals whether the gas came from the mantle, from radioactive decay in the crust, or from some combination of the two. Scientists can use these noble gas tracers to reconstruct fluid migration pathways, estimate how long gas has been accumulating in a reservoir, and determine whether deep fluids are leaking to the surface or being effectively sealed. From an engineering perspective, hydrogen-rich environments at depth present unique challenges. Hydrogen embrittles steel, corrodes conventional casing materials, and creates blowout risks that standard drilling systems are not designed to handle. Future wells targeting hydrogen resources will need specialized alloys, continuous monitoring systems, and real-time geomechanical control to operate safely. The exploration community is beginning to organize around two end-member play concepts for natural hydrogen. The first involves ultra-deep organic hydrogen kitchens, where over-mature marine shales generate thermogenic hydrogen simultaneously with late-stage methane cracking, potentially forming mixed gas accumulations at extreme depth. The second targets basement and fault-controlled systems in which serpentinization, radiolysis, and mantle-derived fluxes supply hydrogen to traps above ultramafic or highly radioactive crystalline rocks. Natural hydrogen commonly co-occurs with deep hydrocarbons not because they share a common origin, but because independently generated fluids exploit the same fault networks, the same lithologic contrasts, and the same trapping geometries. The plumbing is shared, even if the source kitchens are different. What's clear is that the old image of the deep crust as a dead, dry, static environment is not just outdated, it's fundamentally wrong. And that brings us to the surface, because what's happening above these deep systems might be just as important as what's happening below. In 2014, something strange appeared in the Kola Peninsula of western Siberia. A hole. A massive hole. Not a sinkhole. Not a natural cave. A cylindrical crater, more than 50 meters deep, with walls of exposed permafrost and a rim surrounded by ejected soil and ice thrown hundreds of meters in every direction. It looked like something had exploded from below, because something had. Since that first discovery, 8 of these giant gas emission craters have been found in the Yamal and Gaidan peninsulas. They are formed by powerful underground explosions that blast frozen ground and ice into the air, leaving vertical cylinders tens of meters wide punched into the permafrost. And for more than a decade, scientists struggled to explain them. Theories ranged from meteor impacts to collapsing ice caves to methane hydrate dissociation. None of them fully worked. And one puzzle remained. Why only here? The Yamal and Gaidan peninsulas sit within the vast Arctic belt of continuous permafrost. Similar permafrost exists across Alaska, Canada, Scandinavia. But the craters only appear in this one region. The answer, it turns out, connects everything we've been talking about. The Yamal and Gaidan peninsulas sit directly above the West Siberian hydrocarbon province, one of the largest natural gas reservoirs on the planet. The permafrost in this region is up to 500 meters thick, far thicker than in most of Alaska or northern Canada, where it's typically a few dozen to 100 meters. Beneath that frozen lid, enormous quantities of methane are stored, both as free gas and as methane hydrates, ice-like structures where methane molecules are trapped inside cages of frozen water. The permafrost acts as a seal, a cap holding all of that gas in place, and it has been doing so for thousands of years. But now, the seal is weakening. Western Siberia has experienced unprecedented warming since the Little Ice Age ended roughly 200 years ago, with an exceptional increase in the frequency of warm extremes over the last 4 decades. As temperatures rise, the permafrost thaws, not everywhere at once, but in specific weak spots. Below lakes and rivers, structures called taliks form, columns of unfrozen ground that can penetrate through the permafrost and connect the surface to what lies beneath. These taliks tend to align with geological faults, zones of weakness in the rock below, and where taliks meet thinning permafrost, a pathway opens. Heat and gas from deep underground begin to rise. The new model proposed by researchers at the University of Oslo suggests that the craters form through a specific sequence. Gas and heat from deep below the permafrost, from the same kinds of deep geological systems that Kola and KTB revealed, migrate upward through fault-controlled pathways. The heat melts the permafrost from below, thinning it. Meanwhile, the gas builds pressure beneath the frozen lid. As the climate warms from above, the permafrost thins further. Eventually, the pressure exceeds what the remaining frozen ground can hold. The lid fails, and the result is an explosion that ejects soil and ice across the tundra, leaving behind a gaping cylindrical crater. This model explains why the craters are found only in this region. It requires a specific combination of factors: thick but weakening permafrost, abundant gas supply from deep geological sources, fault-controlled pathways connecting the deep subsurface to near-surface zones, and climate warming to trigger the final collapse. That combination exists in the Yamal and Gaidan peninsulas. It doesn't exist, at least not in the same configuration, anywhere else in the Arctic. But the craters might just be the visible symptom of a much larger process. The Arctic permafrost stores an estimated 1,700 billion metric tons of carbon, mostly in the form of methane and organic matter. As that permafrost degrades, methane is released. And methane is a greenhouse gas far more potent than carbon dioxide over short timescales. The release of methane from thawing permafrost is what climate scientists call a positive feedback loop. Warming causes thawing. Thawing releases methane. Methane causes more warming causes more thawing, and on it goes. The craters are dramatic. They are spectacular evidence of what happens when deep gas meets a failing seal. But researchers believe there could be many more of these features hidden across Siberia, disguised as ordinary lakes. Because after a crater forms, it fills rapidly with water and sediment, becoming indistinguishable from the countless thermokarst lakes that dot the Arctic landscape. The craters we've found may be only the ones we caught in time, and the processes at the surface don't stay at the surface. Research published using 9 years of atmospheric data from the Tiksi Meteorological Observatory in northern Siberia has revealed something remarkable about how Arctic rivers are changing the atmosphere itself. The Lena River, one of the longest rivers on Earth and one that flows entirely within Russia, empties into the Arctic Ocean carrying enormous quantities of dissolved organic matter, dead leaves, soil, nutrients, and biological material washed off the Siberian landscape. When this material hits the ocean surface, it releases gases, volatile organic compounds that react with sunlight and atmospheric chemistry to form tiny particles called aerosols. These aerosols serve as seeds for cloud formation. The research found that when air masses travel over ocean regions enriched with this river-borne organic matter, the rate of new aerosol particle formation increases by 300%. Particle growth rates increase by 60%. The result is more clouds, brighter clouds, clouds that last longer and reflect more sunlight back into space. In principle, this is a cooling effect. But the full picture is more complicated. Over bright ice surfaces, additional clouds can actually trap heat. And as the Arctic warms, more rivers flow, more organic matter enters the ocean, more aerosols form, and the atmospheric chemistry shifts in ways we are only beginning to measure. Approximately 11% of the ice-free Arctic Ocean surface is enriched with this river-derived organic matter during summer. In the Siberian sector, that figure rises to nearly 50%. It is a major source of Arctic aerosol that atmospheric models have largely overlooked. And beneath the ice, even stranger things are emerging. In 2018, scientists thawed a chunk of permafrost that had been collected from a site along the Kolyma River in northeastern Siberia. Inside it, frozen in the sediment from a burrow once home to Arctic gophers, roughly 130 feet below the surface, they found a worm, a nematode, microscopic, unremarkable in appearance. They warmed it up. It moved. It crawled out of the thawed sediment and started reproducing. The worm was 46,000 years old. This was not a fossil. This was a living organism that had been in a state of suspended animation called cryptobiosis since the late Pleistocene, since a time when Neanderthals still walked the earth. The species, named Panagrolimus colymyensis, after the river near which it was found, was entirely new to science. It carries 3 sets of chromosomes instead of the usual 2, reproduces without males, and had survived by converting its cellular fats into a sugar called trehalose, which stabilized its cell membranes and proteins through tens of thousands of years of frozen stillness. Scientists compared its genome to the well-studied laboratory nematode Caenorhabditis elegans and found that many of the same genes involved in surviving extreme conditions were present in both species. The genetic survival kit had been conserved for 46,000 years. The researchers were able to induce the worms to enter and exit cryptobiosis in the lab using mild dehydration, followed by freezing. And when they applied the same technique to C. elegans, a modern species, those worms also survived deep freezing for over 480 days, far longer than previously documented. Not everyone was immediately convinced. Some scientists raised concerns about possible contamination, questioning whether the nematodes might be modern organisms that somehow infiltrated the sample rather than truly ancient survivors of the Pleistocene. But the research team pointed to the sterility protocols used during collection, to the radiocarbon dating of plant fragments found in the same sealed burrow, and to the genetic distinctiveness of the species itself. The worm's genome showed it was triploid and parthenogenetic characteristics consistent with a lineage that had been evolving in isolation. The genetic analyses were described as solid by even skeptical observers. And the fact that the worm belonged to a previously unknown species made modern contamination far less plausible. What makes Panagrolimus colomayensis so scientifically valuable is not just how long it survived, but how it survived. The trehalose-based protection system, the metabolic preparation that precedes freezing, the stabilization of key molecular structures, these mechanisms hold practical relevance for fields far removed from nematode biology. Better understanding of how cells and tissues can be preserved in a frozen state could transform biobanking, improve protocols for storing transplant organs, and reduce reliance on the chemical additives currently used to keep research samples viable. The permafrost, it turns out, has been running its own cryopreservation experiment for 46,000 years, and it worked. The implications reach far beyond nematode biology. Understanding how these organisms protect their cells during cryptobiosis could transform how we store living materials, from transplant tissues to research samples. And as the Arctic warms, the permafrost that has kept organisms like Panagrolimus colomayensis frozen for millennia will continue to thaw, releasing ancient life forms, ancient microbes, and ancient genetic material back into modern ecosystems. And beneath the permafrost of Greenland, the past is buried even more deliberately. In 1959, the United States Army built Camp Century inside the Greenland ice sheet. It was a fully operational base, housing up to 200 people more than 100 feet below the surface. It had trucks, it had railways, it had a nuclear reactor. Officially, it was a research station. Unofficially, it was the testing ground for Project Iceworm, a classified plan to deploy nuclear missiles on hidden railway tracks beneath the ice, aimed at the Soviet Union. The idea was extraordinary. Hundreds of miles of rail lines inside the ice sheet, atomic-powered trains carrying nuclear warheads through snow tunnels between concealed launch stations. A shell game covering an area the size of Alabama. It never worked. The ice sheet is not static. It moves, deforms, and compresses. The tunnels buckled, the tracks warped. Project Iceworm was rejected by NATO in the early 1960s. The Army abandoned Camp Century in 1967, leaving behind everything they couldn't easily remove: diesel fuel, PCBs from electrical equipment, low-level radioactive cooling water from the nuclear reactor, asbestos, lead paint, human waste, all of it left in the ice, under the assumption that perpetual snowfall would bury the camp forever. That assumption no longer holds. Greenland's ice sheet is melting. Climate models suggest that Camp Century could be uncovered by the end of this century. And even before the camp itself is exposed, meltwater from increasingly warm summers is percolating down through the ice, finding cracks and crevasses, and potentially reaching the buried waste. From there, contaminated water could flow through under-ice channels to the coast and into the ocean. The question of who is responsible for cleaning it up remains unresolved. The camp was built under a treaty between the United States and Denmark, which then governed Greenland. The waste was left behind by the US Army. But the ice that was supposed to entomb it forever is being melted by a global climate problem that no single country created alone. Greenland's ice sheet holds enough water to raise global sea level by 24 feet if it all melted. The permafrost beneath the island is destabilizing infrastructure, including the critical radar installation and runway at what is now called Pitufik Space Base, formerly Thule Air Base. Mountainsides are crumbling as the ice that held them together disappears. Bridges that stood for 50 years have been swept away by floods fed by meltwater. And somewhere buried under all of that ice and rock and frozen ground, the deep earth continues to do what Kola first showed us it does. It circulates fluids through fractured crystalline rock. It generates heat and hydrogen and methane. It drives chemical reactions that fracture stone and redistribute metals and sustain permeability at pressures that should crush everything shut. It is alive in a way that defies the sterile models of the 20th century. The Kola Superdeep Borehole was sealed and abandoned in the early 2000s. The site today is a ruin, a collection of decaying Soviet-era buildings on the frozen tundra, a rusted metal cap over a hole that goes deeper into the earth than anything else humanity has ever made. The scientific data it produced filled volumes, but in a sense the most important thing it ever did was prove how wrong we were about the deep earth, about what's down there, about what it's doing. The Chinese are now drilling past 11 kilometers and finding commercial gas where none should exist. Researchers are pulling living organisms out of 46,000-year-old permafrost. Siberian craters are blasting ice into the sky because deep geological gas can no longer be contained by a warming lid of frozen ground. Rivers are changing the Arctic atmosphere in ways climate models never accounted for. And beneath Greenland's ice sheet, a Cold War nuclear base is slowly being released from its frozen tomb by the same warming that is reshaping every system on the planet, above and below. We went down 12 kilometers at Kola and discovered that the Earth's crust is nothing like what we imagined. It is hot, wet, fractured, chemically reactive, and full of surprises. And now the surface is changing too. The ice is retreating. The permafrost is thawing. The seals that held the deep Earth's secrets in place for millennia are beginning to fail. We thought we buried these things deep enough that they'd stay buried forever. The planet, it seems, has other plans.